By now you've seen how to work with, say, planes and lines inside three-dimensional space, and we're ready to move on to slightly more complicated surfaces. So the next level of complication, beyond planes, are quadratic surfaces. We'll want to understand the kinds of equations that describe these quadratic surfaces and what they look like in three-dimensional space. And we're going to start with cylinders. And I'm sure you're familiar with what a cylinder looks like. I mean, you could imagine the outside of a soda can as a cylinder or any sort of objects. And in the XYZ coordinate system, a cylinder is pretty easy to describe if you align, say, the axis of the cylinder along the z-axis. Then the cross section is just a copy of a circle of radius 3 stretching along the z-axis. That means the equation should just be the equation of a circle in the xy plane, and the missing z-coordinate means that that circle equation is just copied along the z-coordinate again and again and again for every value of z. But we want to generalize this concept. We don't want to have to depend on our cylinder being aligned in the z-axis. And what does that equation look like? So the essential is, if you can find a plane of intersection, hopefully a plane parallel to, say, the xy plane or the zy plane or the xz plane, that intersection will give you a curve. And then when you move along a perpendicular variable or axis, you just have a copy of that curve stretched in that direction. So for us, we're going to generalize our interpretation of a cylinder to actually be anything of the form: a set of lines parallel lines passing through a given curve to be called a cylinder. Those lines are called rulers. So this is a much more generalized version of that description. Notice this little wavy curve over here. That is the curve that we're thinking of. Then the rulings are the parallel lines that cross through that wavy curve to make a three-dimensional surface. Here is another example of a cylinder where the cross-section is an ellipse. The rulings, those parallel lines, move along the edge of the cylinder. The book has some examples of other kinds of graphical cylinder surfaces, and at first you may be wondering, it may be hard to identify them as cylinders. There's some signs though. Our three-dimensional space should have three variables, and if our equations are only of two variables, then it will describe a cylinder because it's describing a particular curve on two variables. But in three-dimensional space, the missing variable is just going to be a repeat of that curve stretched along that axis. Notice B does not fit that pattern, but it's still going to describe a cylinder, and you can visually see it if you graph it, which you can just graph it by entering this equation to GeoGebra, but also you can see this picture over here. And the reason why it does have that Z, all three variables, is because it would be a cylinder in the familiar sense, but it's no longer aligned with a plane, an intersection plane, parallel to one of our familiar planes, like the ZX plane or the XY plane or so on. I mentioned this verbally, but that curve that all the rulings go through, that's called a trace. I have another example of a cylindrical surface in GeoGebra. You can identify visually that it should be cylindrical because there's a pretty clear curve that parallel lines go through, the rulings go through. The equation for it is actually written over here, but I also used, the equation for it is written over here. We like cylinders because they're simple enough surfaces where you are actually just describing a two-dimensional curve and stretching into three-dimensional space, at least along an axis. And when we want to do computations later on surfaces, these are the easier surfaces to work with.